Hi everyone, I'm Wafa Namani. Today I'm going to share with you my project, which is about optimizing the treatment regimen for pancreatic adenocarcinoma. So I've been working on this project for 2 years now at the Grimm Lab, which is at Memorial Sloan Kettering Cancer Center in New York City. So I'm really excited to share my experience and also my findings there. So we were looking at pancreatic ductal adenocarcinoma, which is abbreviated as PDAC. It's the most common type of pancreatic cancer. It makes up about 90% of all cases, and it also happens to be the most advanced stage of pancreatic cancer, meaning it's usually spread to multiple locations of the body. And on top of that, the 5-year survival rate, meaning the rate of survival from the point of diagnosis to the 5-year point, is approximately 3%, which is incredibly low. So, pancreatic cancer is an unmistakably fatal condition. And it's characterized by these dense solid tumors. So, I have a diagram of what the tumor microenvironment looks like. And you can see that it's not just the cancer cells, there are other components that make up the tumor. And this makes it difficult for the drugs to actually penetrate through this dense solid mass. So you can imagine that the current treatments that are out there, they're traditional chemotherapies, they're not that effective. They don't get to the cancer cells at a high enough rate. And in fact, they have adverse side effects on the healthy tissues. So it's kind of like a lose-lose situation. Like these chemotherapies, they're not getting to the cancer cells. In fact, they're harming the already healthy tissues. So patients suffering from pancreatic cancer, they have a decreased quality of life, not only due to the fact that they have these tumor masses, but the fact that the treatment is just it causes a decrease in the quality of life of patients. So when we're looking to optimize the treatment regimen, we really want to increase that quality of life as well as increase the lifespan. That's kind of the two things we have to keep in mind. So we're looking at, in terms of like trying to optimize treatment regimens, we're looking at ferriheme nanoparticles. So these are basically iron oxide nanoparticles. I have a diagram here. So it has this iron oxide core. It's basically rust. You can think of it like a little rust core inside. And the outside is like a CMD coating. It's a carbohydrate, like a sugar coating, basically. And it has these little carboxyl groups at the end of it, which give it an overall negative charge. So why we wanted to use ferriheme in our optimization of the treatment was, first, we wanted to use it as a drug delivery agent. So what that means is we wanted to use it as sort of like a transporter of the drugs to the cancer cells. So why it's a good drug delivery agent? Well, first, because of its size. It's a pretty ideal size. It's not small enough that it just goes through your body and it's just like excreted, and it's also not big enough that it's a cause for alarm in your immune system and it's taken up by your liver or spleen. It's not the case. So the size of it is pretty ideal to even like get to the cancer cells. Secondly, it has this very unique pH dependent release aspect, which means that it dissolves its outer coating, meaning its outer coating would ideally have drugs on it too. It dissolves it under a low pH setting, which is conveniently found in the tumor microenvironment of the pancreatic cancer tumors. So that's pretty convenient for us. So it only specifically releases its drug in that sort of tumor environment. So that's a pretty cool aspect about it and why we wanted to use ferriheme. I have this diagram of an M&M basically to represent an iron oxide nanoparticle. So the chocolatey core inside is sort of analogous to like the rust iron oxide core, and the sugary coating is sort of like the CMD coating. So you can think of like ferriheme or iron oxide nanoparticles as M&Ms. Secondly, we wanted to see if ferriheme nanoparticles could generate ROS. ROS is reactive oxygen species. So really all cells have a certain level of ROS. This helps them with cell growth and division, which is known as proliferation. And cancer cells, they generally have higher levels of ROS because they grow and divide more rapidly than healthy cells. So this is actually beneficial for them. So if we exceed that threshold between healthy and toxic levels of ROS, then we can actually induce cell damage and a specific type of cell death, which is known as ferroptosis. So if you've heard of apoptosis, which is cell suicide, it's pretty similar to that. Ferroptosis is an iron-induced cell death. So we wanted ferriheme, which has iron in it, to basically induce this ROS via the Fenton reaction, because we've seen in previous studies that iron can actually generate ROS that can lead to cell damage. So for our experimentation, we used an MTS assay, which measures viability. How many of the cells are alive, how many of them are dead. We treated cells, pancreatic cancer cells, with drugs, different types of drugs, with or without ferriheme. So we wanted to compare how does viability change with or without ferriheme. Next, we did a flow cytometry assay. This is basically to measure ROS. So this is a very sophisticated method to measure ROS in each of the cells. So this is what the output looks like. This is a picture of me basically plating the cells for our experiments. The next part of my project was actually looking at how to functionalize the surface of the nanoparticles. So when I did this project last summer, I found that not enough of these nanoparticles were actually entering the cancer cells. So I wanted to use sort of like some sort of conjugation, basically like an attachment onto the surface of the nanoparticles to basically increase the cellular uptake. So unfortunately, I wasn't able to carry this out because due to the restrictions of COVID-19, but this looks really promising, and I hope that this is something I look into in the future. Next, I want to show you all tell you about my first experiment. So this is the first ever experiment that I did in my lab. And so here I just treated some cells with ferriheme and drug, like the drug with or without ferriheme. And I was actually getting this ready for a flow cytometry analysis. And basically, this takes a really long time. This took me like 8 hours to do. And like in between, we need to do washes, which means that we need to take out this media in a very careful manner as to not take out the cells. And during one of my washes, I just stopped to look in the microscope, which is not even like part of the protocol. And I saw that I had suctioned out all of my cancer cells. So I had to basically like throw out this plate. And it was kind of disappointing. I was really sad about it. This was my first experiment, and it was a complete failure. But you know, it's fine. Like now that I look back at it, it was like such a little failure. And this wasn't even my only time that I failed. I failed so many experiments, but that's okay. I encourage anyone that's interested in STEM to really go after what you want. Go pursue things in research in whatever field it may be. And lastly, I'd like to give some acknowledgments to some mentors who have helped me along the way. Firstly, Dr. Victoria Schulman, who is the director of the Aspire program. She really helped me get on my feet and find this lab and start my research project, and she really guided me through each step. She helped me become a better scientist for it. And Elizabeth Isaac, who was my mentor at the Grimm Lab, she really guided me through each step as well. She mentored me and she taught me all of the experiments and the assays and how to do the analysis. And Dr. Jan Grimm, who was the lab head, I'm really thankful that he let me into his lab, let me use his resources. And Dr. Elise Sonai, who helped me with the flow cytometry and the analysis of it, which was pretty intricate, and I couldn't have done it by myself. And Dr. Paul Weinstein at the Stanford Hospital, who's an oncologist there, and he gave me a really good overview and helped me contextualize my own study. I was able to meet with cancer patients and get a better sense of why I'm doing this project, who I'm doing it for, and really served as a great motivation for me when I look at my own study. So I'm really thankful that I had the opportunity to do that. And lastly, I'd like to thank my Aspire class for their continuous support, their helpful feedback throughout my presentations, and just always being there for me. Thank you all for listening. And if you have any questions or you'd like to continue the discussion, please feel free to reach out to me. Um, I'd love to talk more about this.